Okay, we are going to talk about building structured lateral load resisting systems. And we are going to look at different lateral load resisting systems, distribution of lateral loads in horizontal lateral load resisting systems, distribution of lateral gravity load in vertical lateral load resisting systems. Let's look at different lateral load resisting systems. We have different lateral load resisting systems in the vertical and horizontal planes. In the vertical plane, we usually use one of the following lateral load resistance systems. Either we use shear walls, brace frame, moment resisting frame or rigid frame, dual system, and also we can use the lateral load resistance enhancement devices, which mostly they are used for seismic areas. And also in the horizontal direction, all of the above were in the vertical plane, but in the horizontal plane also we have the diaphragm at the floor or roof plane, which can be in the form of a concrete slab or a metal deck, or we can have horizontal trusses within the floor or roof plane to just stiffen up the diaphragm. Then we are going to first look at the vertical plane lateral load resistance systems, and we start with shear walls. Shear walls generally are vertical cantilever walls, which are designed to take the load from the floor or roof diaphragm and transfer and transmit it to the ground through shear. Then if I am looking at the elevation of a shear wall, the inertial forces from the earthquake that we normally show it what mass times acceleration is acting at the floor or roof, and that can be either inertial force or it can be wind force, in general lateral forces. Then it goes to shear basically and transfer the load to the ground. Then the shear wall basically is acting in shear and taking the shear force from the lateral force and transfer it to the ground. To be effective, shear walls must be continuous from the top of the building to the foundation without any offset or minimum opening. Then what you want is that basically if you have got a multi-story building, you don't want to stop your shear wall here, because then your lateral forces are going to basically get concentrated right at the bottom of the building, and you are going to have damage in this column. Then it's not a very efficient system, and especially for seismic zone, we want to make sure that the shear walls continue all the way to the ground, and we don't want to have any breakpoint there. It is also it's most efficient to locate the shear walls around the building perimeter to maximize their torsional resistance. Then basically if you have got any shear wall, it's the best to basically place them in the perimeter of the building, so that if you have got any twisting or rotation of the building, they can provide the most resistance. You don't want to place your shear wall within the building, inside the building, but there are limitation within the building. You may not be able to put shear walls right around the perimeter of the building, because they have to be open for the architectural requirement. Then depends on the situation basically. Now this is basically a building with two shear walls, and as you see, the shear wall provide basically a shear resistance or lateral force resistance in the plane of the wall. Then this wall is only can provide resistance against the forces that coming within its plane. Perpendicular to it, if you have got a load perpendicular to the wall, it cannot really provide any resistance, or it can provide very little resistance. Most of the resistance of the shear wall is provided within their own planes. Then it would be better not to consider these forces perpendicular to the shear wall. And in this case, we have got a core wall that basically provide shear resistance in both directions. In this direction, these two walls, basically, if you are looking at this direction, which the forces are shown here, then this shear wall is going to basically take the load. And if you have got forces in this direction, these walls are going to be able to provide resistance within their plane. Now, let me show you a few animation on the shear walls basically here, and also core wall, how they behave under the lateral load. Let's first look at the shear wall here. As you see here, the forces coming from the left to right are resisted by this shear wall, and this reaction at the base of the wall, you can see it is basically resisting the force coming from the left, the shear resistance coming from the right, and also you have got this moment which causes compression on this side of the wall and tension on this side of the wall. Then you have got this moment at the base of the shear wall which is resisting it. And that is basically the support reaction. Now let's look at a core wall. Then if we have a core wall and we have got again lateral forces, you see the same thing basically. Since the loads are coming from left to right, then the shear resistance is from right to left, and you have got also a moment at the base of the core wall. Now the next vertical lateral load resistance system is brace frame. Brace frame are the most economical basically vertical plane lateral resisting systems, especially for a steel structure. Brace frame are typically used in a steel structure, and they can act as a stiff lateral force resisting system like shear walls, which shear walls are also very stiff. And they can basically provide both shear resistance and also a stiffness. However, the stiffness of the shear walls generally are larger than brace frame. They have, however, larger ductility than shear walls. Then the ductility of brace frame is larger than generally the shear walls. Steel bracing, they can be made out of rolled section, or it can be circular board or tubes. Then we can use I shapes, for example, or you can use angles. You can use angles, or you can use the tubes for the bracing in brace frames. They can be designed in a variety of configuration depending on the forces that they have to be resisted, and also architectural limitation. We have generally two types of brace frame. We have got concentric brace frame and eccentric brace frame, which we are going to talk about them in more detail in the next few slides. This is a concentric brace frame. Now, why we call it concentric brace frame? Because the brace, as you see here, is basically going through the center of the column and center of the beam. Then there is no eccentricity between the location or the center line of the brace, the beam and column. They meet all at the same location, and you can see it also here. If I'm, let me change the color, then the center line of the brace, the center line of column and the center line of beam, they pass through the same location. There is no eccentricity here. This is why we call it concentric brace frame. Now, as I said, brace frame generally they provide large stiffness, but they are not as ductile as other lateral force resisting system, mainly moment frame that we are going to talk about. But the main problem or main disadvantage of brace frame is the point that we have. Once we put the braces within the area, then we cannot put a door or window. Then obstruction of a space is basically the problem, which is the same problem for also shear walls. Then shear walls and brace frame, they have got the same problem. However, brace frame are very economical in terms of providing lateral load resistance system, and depending on the configuration, you may be able to also accommodate windows windows or doors, and especially once we look at the eccentric brace frame, we will see that it is possible also to place easier door or windows in that type of system. These are different configuration of concentric brace frame. As you see, for all of these systems, the center line of the brace, center line of the beam, and center line of column pass through the same point. Then all of them, they pass through the same point. This is why it is called concentric brace frame. And these are different shapes of that. Here we have got X bracing. This is diagonal bracing, chevron bracing, and K bracing. In the X braced frame, if your loads, for example, are coming from the left to right, then these members are going to be in tension. These members are going to be in tension, and the other ones are going to be in compression. Then the other braces are going to be in compression. This is going to be in compression. This is going to be in tension. Then if the load goes the other way, if it comes from right to left, then the direction of these forces are going to switch. Then the tension members become compression, compression members become tension. Then in this case, we have got a sort of symmetric behavior. We don't have the same for the diagonal bracing. We have similar situation also with the chevron bracing and also K bracing. Now, then we have a different category of brace frame called eccentric brace frame. These are a special type of brace frame that the center line of the brace, the beam and column, they do not pass through a common point. The connection of the beams to columns are a moment connection, and for this reason they provide ductility. Since they behave like moment frame, they provide more ductility. At the same time, since they are also brace frame, they provide rigidity, more rigidity than moment frames. Then we have got both ductility of moment frame and rigidity of brace frame within the eccentric brace frame. And that is in fact the advantage of eccentric brace frame, especially when we use them in a seismic zone. In eccentric brace frame, there's a short piece of beam between the ends of the brace, which is called the link beam. And this link beam especially provides large ductility. It goes through a lot of deformation under the earthquake motion, and it can distort and dissipate the energy and protect the remainder of the building from damage. Even though the main advantage of eccentric brace frame is basically its performance in earthquake resistant design, they can be also used to accommodate architectural requirements, for example putting doors or window, as we are going to see it here. Now this is an eccentric brace frame. If my loads are coming from right to left, then this side, this brace is going to be in tension, this brace is in tension, this brace is going to be compression, this brace is compression, and then the column on this side is going to be in tension, the column on that side is going to be in the column on the right is going to be in tension, column on the left is going to be in compression. And then this is how basically the system works. And as you see, these are eccentric brace frame because the center line of the beam, center line of the brace, they are basically are offset. Then the two center line of the braces, they do not pass through the column, and that is why it is called eccentric brace frame. Unlike say a concentric brace frame that it should have looked like this instead of, and if I show you another story, then for a concentric brace frame, as you see, the center line of brace, center line of brace, and center line of beam, they pass through the same point. But in a eccentric brace frame, the center line of the brace, the two braces and the beam, they do not pass through a common point. This is why it is called an eccentric brace frame. But for this eccentric brace frame, we can, for example, place a door easily here, which we couldn't do it if we have it a concentric brace frame, because we have got a smaller space available to place a door. Now, these are different configuration of eccentric brace frame. As you see, this is the link beam that we were talking about. These are the link beam, and they go through large deformation when the building is subjected to earthquake loading. And the connection of the beams to columns are typically moment connection, which provide the ductility of a moment frame, and then we have got braces which create more rigidity for the structure. Then under seismic load especially, we don't have as much damage. And you can see here, because of the configuration of the braces, it is possible to put larger opening than if the same bracing was concentric. This is an eccentric brace frame, details of an eccentric brace frame. As you can see, this is the link beam here, and this link beam, you can see the stiffener plates that we have got here to provide more ductility, because during the earthquake, this area, this link beam, goes through large deformations, and they can dissipate the energy of the earthquake tremendously. Now let's look at a few animation that shows the deformation of the concentric eccentric brace frame under lateral load. Let's first look at concentric brace frame. What you see here is that the load is coming from left to right, and the columns within the brace frame here on the left is going to be in tension. The brace connected in this direction is going to be in tension, and the brace in the opposite direction is going to be in compression. And this column on the right also is going to be in compression. Then, as you see, this is how it will work. Then basically this column is going to be pushed, then the reaction is going up. This column is going to be pulled, then the reaction is going down. Then that is how basically a concentric brace frame acts when it's subject to a lateral load. Now let's look at eccentric brace frames. And as you see, with the eccentric brace frame, we have a similar behavior. Again, the columns on the right, they are compression and the braces connected to them, and the column on the left, they are in tension along with the braces connected to them. And since the column on the right is in compression, then the reaction for the column is going up, and the other side is going down. We have the column is going to be under an uplift basically. Now let's continue with the other vertical lateral load resisting systems. The next type of system that we are going to look at is called simple frame and moment resisting frame. First, let's look at simple frame. The simple frames are only able to take the gravity loads. They are not stable against lateral loads. Let me just show you the simplest simple frame possible. Let's suppose that we have a one-story structure, and it is a pin connected. Now, if this building is subjected to a gravity load, then the beam can deflect. Now, as you see here, the connection of the beam to column are pin connection, or we call it simple connection or shear connection. Then let me write down here. This is a pin connection, pin or simple or shear connection. Now, in this type of connection, basically the beam is connected to the column such that when the beam bends, the column does not bend with it. Therefore, for this type of simple frame, the frame is going to be stable because it is subjected only to gravity load. But if the same frame now it is subject to lateral loads, then if it's subjected to lateral loads, then this frame is going to basically be unstable. It cannot take the lateral loads. Then it is stable against gravity loads or the vertical loads, but against the lateral load, it's unstable. The main advantage of simple frame is their simplicity in terms of connecting it together and basically creating the simple frame, and also the fact that they can take gravity loads without any problem. And since the structure is simpler to basically put together and make simple frame, it is going to be cheaper. Then we want, in fact, to use as many simple frame as possible in a building, but the problem is that they are not stable against lateral load, which means we have to always use the simple frames in combination with other framing system. We cannot just use simple frames because they cannot take lateral loads. Now, this is in fact a simple or shear connection or pin connection that we were showing ideally on the right. In reality, how it is made. Basically, we take the beam and connect the flange of the beam to the column. It can be to the flange of the column or to the web of column. As you can see here, we have got here an angle on this side, an angle on the other side, and bolted to the web of the beam and bolted to the flange of column. Then this is basically a simple or shear connection. The important thing is that only the web of the beam is connected to the column, and the flanges are free. The flanges are free. The flanges are not connected. Then, as I said again, the simple frames are not stable when subject to lateral loads. They have to be used in conjunction with a lateral load resisting system, but they are very simple to make, and therefore they are very economical for supporting the gravity loads. Now, on the other hand, we have got moment framed or rigid frames, which we have got moment or rigid connection for them. Now, the main difference between a moment connection and a simple connection is that the flanges of the beam are connected to the column. In this case, for example, we have got a plate that is welded to the column, welded to the column, welded to the column, welded to the column, and then the beam is connected to the column by connecting the web of the beam, bolting the web of the beam to the column, and also bolting the flanges of the beam to the column. In this case, we have got a rigid or moment connection, which results in the fact that the frame can take lateral forces. Then let me just draw it here. Suppose we have got the same frame, and this shouldn't be. Then this is a moment frame. And subject to gravity loads, this frame is stable and it can deform like this. This is under gravity load. Now, under lateral loads, under lateral load, then this frame is going to bend like this, which again is stable. Then for lateral load is also stable. Then both gravity load and lateral load can be resisted by the moment frame. Then, as I mentioned before, the flanges of the beam are basically restrained to the column so that the rotation of beam is transferred to the column. As you see here, when the beam bends, the column bends with it. When the beam bends, the column bends with it, which was not the case when we had a simple frame. And the connection typically are done by either bolting it as shown here or by welding it. You can directly weld the flange of the beam to the column, which we are going to look at later here. Reinforced concrete connection are normally designed as moment connection. Then typically for reinforced concrete, we expect to have moment frames or moment connection. Still, moment connection are more expensive than simple connection due to the field work, because when we have got the flanges are connected, then we need to basically connect also the flanges, and especially if we need to do field welding, then it become very expensive to create moment connection, having moment frame. Therefore, we try to minimize the number of moment frame and moment connection within a building, just to have a few rows of them if necessary, or if we need to have brace frame, just minimize the number of them. We don't need to put brace frame or moment frame in every bay. We try to put as many simple frame as possible, and then few moment frame or brace frame in each direction to be able to take the lateral loads. Now, moment resisting frames or rigid frame are architecturally much more appealing than, say, a brace frame or shear wall, because they provide more unobstructed spaces than compared to a moment frame looks like this. But if you have got a brace frame, you have got a bracing here, and this bracing is going to occupy a space, then architecturally it might be a problem. In general, moment frames or rigid frame, they provide the most architectural design freedom. Moment resisting frame generally carry the lateral load primarily by flexure in the members and joints. As I showed you before, and let me just again show you, if you have got lateral loads here, then this frame basically is going to bend like this, which means that it's basically resisting the lateral load through the bending of the beams and columns. Joints are designed and constructed to be rigid, which means that they can transfer moment between the column and beam. Generally, the largest stiffness among these vertical lateral resistance systems that we looked at, the largest stiffness belongs to shear walls. After that, we have brace frame, and after that we have got moment frame. In terms of ductility, it's just the other way around. The moment frame or rigid frames, they have the largest ductility. After that we have brace frame, and after that we have shear walls. Then remember that shear wall, they provide the largest stiffness. After that is brace frame, after that moment frame, but the other way around is for ductility. Moment resisting frames are much more flexible than brace frame and shear wall. Just let me just show you again. If this is a moment frame and comparable, say, brace frame, we have got pin, and then brace frame here. Under lateral loads, the moment frame, under lateral loads, the moment frame is going to have large lateral movement, lateral deformation, because it is not as rigid as, say, brace frame. But under the same lateral force, the brace frame is going to move but much smaller amount, which means that the brace frame is much more rigid than the moment frame. The moment frame can have very large lateral movement, or what we call it as drift. Just draw this better. Then this is the lateral movement of the building, which we call it drift. And for moment frame, that can be a problem, and one has to basically design the structure so that the lateral drift of the building does not cause discomfort of the occupants, or it might not damage non-structural elements under wind. For example, if you have got large wind, the building can move too much and it might cause failure of the cladding. If you have got, for example, glass cladding, it may pop the glass. Moment resisting frame, generally they have high ductility, therefore they can withstand much larger load without complete failure. This is very important, in fact, if you are designing the building in seismic area. This is why in general moment resisting or rigid frames are more popular in seismic prone areas. This is basically the moment frame. As you see, the frame is resisting the load through the bending of the column and beams. Is resisting the load through bending of columns and beams, and this is in fact a typical framing plan of the building. Now, before I talk further about the details of this plan, let me just show you an animation of moment frame. And as you see here, it's sort of deformation or exaggerated here so that you can see it better. You can see the loads are coming from left to right, and you can see that the beams and columns, they are deforming to take the lateral loads. Again, as you see, the shear is in the column, is in the opposite direction of the applied load, and you can see also the moment that you have got at the base of the building basically. Now let's go back to the plan here. Now this is a plan of a 5-story building. On the left you see the elevation, on the right you see the framing of it. Now we typically show the moment connection with placing an arrow here. Sometimes people that also show the moment connection at MC on the drawings. Then as you see here, if I look at this and assume this is the north-south direction, you can see that in the north-south direction we have got lines 1, 2, 3, 4. Now remember, when the load is coming in the north-south direction, only the frames that they are parallel to that force are resisting the load, which means that if I have got load in the north-south direction, only frames along line 1, 2, 3 and 4 can take the load. Lines A, B, C and D, they do nothing. They cannot really resist the lateral load. Now since we have got simple frame along lines 2 and 3, they are not going to be able to take the lateral loads. Then all the lateral loads through the concrete slab, which is going to be very rigid. Remember, the concrete slab is going to be very rigid. It's going to transfer the load to these two moment frames along line 1 and 4. Then basically the simple frames along line 2 and 3, they are leaning on the moment frame along lines 1 and 4 to take the lateral loads. Then basically the loads in the north-south direction are resisted by the frames along line 1 and 4. Line 2 and 3, which they are simple frame, they are basically leaning on moment frames along line 1 and 4. Now in the east-west direction, if the load is coming in the east-west direction, then frames along line A, B, C and D are taking the lateral loads. Again, along line B and C we have simple frame, and we have moment frame along A and D. Then the load hits the building, can be wind or earthquake, gets to the floor. Now we have got a concrete slab, and the concrete slab basically transfer the lateral load to these two frames along line A and D, and they take the lateral loads. The simple frames, they just lean on these two frames to take the lateral loads. Then these simple frame along line B and C, they can take the gravity load, but they cannot take lateral load. All the lateral load are going to be transferred to these two frame along line A and D to be resisted and be taken and transferred to the ground. Then this is how typically is done in a building. We have to have a lateral load resistance system in each direction. Then we have to look at it in the north-south direction. Then we have along line 1 and 4 moment frame, and in the east-west direction we have got along line A and D moment frame that they are taking the lateral loads. Now instead of moment frame along line A and D, we may be able to put brace frame. It is possible, instead of putting moment frame, to put brace frame. Then in the north-south direction we can have moment frame along line 1 and 4, and in the east-west direction we can have brace frame along line A and D. It is also possible to do that. Again, depends on architecture requirement. If the architects allows us to basically use these bays to put brace frame, fine, then we can basically do it this way. But if there is no preferences and we can put any lateral load resistance system, it's preferable to put a brace frame everywhere basically. Then it would have been probably the most economical to basically put brace frame along all these bays. And depending on the amount of load, we might need to put only on 2 bays, or we can put also extra if the load is larger. But if we need to basically make sure that the exterior is going to be clear and no obstruction, then we need to remove the brace frame and use the moment frame all through the building, and this way we have got wide open areas all around the building. Now let's look at different type of moment resisting frames according to the International Building Code, and these are mainly related to seismic design. First, the special steel and concrete moment frame. This frame, they must be especially detailed to provide ductile behavior and comply with the IBC provision for seismic design. Now, this ductile behavior in seismic area is very important, and the reason is that when we design the building, generally we cannot make them earthquake proof, which means that if the earthquake load is very large, if the earthquake is very strong, then the structure may get into the plastic behavior, it become inelastic, it can deform, but we don't want to disintegrate. That is when ductility become very important, which means that we want to building to flex and bend, and that bending can be permanent, but it doesn't cause the complete failure of the building, because that is going to cause fatalities. This is why we don't want the entire structure fail. We want to basically go through a lot of deformation, but it doesn't fail completely. This is where ductility becomes very important. Then ductility is why it's very important factor in seismic resistance of structures. The other type of moment frame are intermediate and ordinary moment frame. These kind of steel and concrete frames, they have less strict restrictive requirement than a special moment resisting frame, and they can be used, and they do not provide that much ductility, and they can be used in areas that the seismic activity is not much, and we do not expect to have very large earthquakes. There are other types of moment resisting frame, such as a special composite moment frame, intermediate and ordinary composite moment frame, and a special steel truss moment frame. We'll talk about more types of this framing system later in terms of the seismic requirement. One important point that you should remember is about the changes to the moment connection design following the 1994 Northridge, California earthquake. In the aftermath of the 1994 Northridge earthquake, a large number of buildings with the moment resisting connection that we have got here, they have been damaged, and the connection that have been cracked. Basically what happened after the earthquake, they found that in many of these steel structures which they had this type of connection, they had cracks going through the column and through the web. Now, how is this connection made? This is a moment frame that basically the beam is connected to the column by using an angle welded to the column and bolted to the beam, or can be welded to both of them, and then the top and bottom flanges of the beam are directly welded to the column. Now, for the top welding here at the top of the beam, welding is sort of straightforward. These are field welding. Basically they could weld this in one pass. They could go at the top of the beam and weld it in one pass. But for the bottom weld, it is not possible to weld the entire flange to the column in one pass. Then they needed to weld it in one side, then the welder goes to the other side and weld the rest of it. This is done in the field, and that caused the sort of defect in the weld that they had at the bottom flange, which basically caused cracking and rupture through the column and through the beam. And since this, especially the fracture within the column, can cause global failure of the building, this was very significant, and they basically decided to change this type of connection to make sure that the failure does not happen within the column, because failure of the column, as I mentioned, can create global failure, complete failure of the building. Now, after that earthquake, after studying all of this building, the building code made changes to the type of connection here. They come up with what is called a dog bone or reduced beam section connection. Now, the way that moment connection was changed was that in the beam, we basically cut part of the flanges at the top and bottom before we get to the connection. Now, when the building goes through large deformation due to an earthquake, then this zone, this portion of the beam becomes weaker, and all the deformation can happen within the beam. And if there is any failure or rupture, it's going to happen within the beam, and it's not going to happen in the column. Failure of the beam can be local, but failure of column is going to be global. And this dog bone connection or reduced beam section RBS connection basically was the fix for the type of moment connection that had been widely used in seismic areas. This shows a photo of a dog bone connection. As you can see, the flanges, the top and bottom flanges of the beam, they are cut so that they provide sort of a weakness within the beam rather than the column. As you see here, the flanges of the beam are welded to the column. The weld at the top is in one path from the top of the beam. That's going to happen, and for the bottom flange, again, welding is done on one side, and then they go to the other side and weld the rest of it. Now let's look at a dual system. A dual system are basically a combination of two different lateral load resisting systems within the same direction. For instance, if we have a moment frame and shear wall which combines the ductility of moment frame and rigidity of the shear wall, they can be a good system. These systems had been used in both seismic and non-seismic areas. For high performance, there is an increased use of dual systems such as shear wall cores with perimeter moment frames. For example, here, as you see here, this is the plan view of a building which has dual system. In the north, south, or east west direction, if you are looking at it, say in this direction, we have got moment frame along this line. Let me call this line 1, 2, 3, 4. Then you can see along line 1 and 4 we have moment frame, and along line 2 and 3 we have got shear wall. Then in this direction we have got both moment frame and shear wall acting in the same direction to take the lateral forces. This is why this is called a dual system, because there are two different systems within the same direction resisting the lateral forces. That can be also a very effective approach where you want to have clear opening around the building, and you can put all the circulation like elevator shaft and stairs within the core. Then you can have a concrete shear wall, or you might have a brace frame in the middle of the building, all around the building to have moment frame, and this becomes also very ductile in terms of resisting lateral forces, because you have moment frame, and also very rigid because of the shear walls, and also it's very practical system to use. The last part is lateral load resistance enhancement devices, and there are three main devices that we are going to look at here. And the first one is base isolation system, BIS. The next one is added damping system, ADS, and the last one is tune mass damper, or TMD. Now, the base isolation system that has been used in many structures, and we are going to talk in more detail later, is basically the system that the superstructure of the
building is partially isolated from the ground motion by the use of bearing, generally consisted of a special formulated rubber and a steel laminate with the central core of lead. Basically, the idea is very simple. Since the earthquake force is transferred through the ground to the building, then we want to isolate the structure from the ground. If we can basically effectively isolate the building from the ground laterally, then the ground can move, but the building cannot move or does not move. That way, we can basically keep the building intact and there won't be any damages. For doing that, we have got these base isolation devices that basically are used at the base of the building between the column and the foundation, and that provides basic isolation between the structure and the building. These base isolation devices look like this. In fact, this is the base isolation device that you used in Oakland City Hall in California. This is the column in the building up above, and this is the base plate, and this is the pedestal that goes on the foundation, and these are the base isolation devices that we have. Let's look at it more closely. The base isolation devices are made of layers of a steel plate, high yield steel plate, and rubber that they are very rigid and they are put together in layers. And then in the center we have got a lead core. Now what happens is that the lead can dissipate the energy of the earthquake when it goes through lateral deformation and turn it into heat, and the rubber and a steel plate, they become very rigid and they can take the gravity load very easily. Then this system can go through large lateral deformation, and a steel can provide large vertical force resistance, and at the same time very little deformation is transferred to the structure, and little basically movement of the ground is transferred to the building. This is how it isolates the structure. The base isolation has been used for the rehabilitation of historic structure. This option has been used as it produces the costly and damaging structural changes. For example, if you want to put bracing or you want to add shear walls, it's going to be a major change in the building, and it's going to be much more costly than providing just an base isolation within the structure, which is going to happen at the base of the building. You don't need to open the entire structure. It also reduces the non-structural and content damage relative to the fixed system, and the reason is that when you have base isolation system, the building is not going to move much. Therefore, the content of the building is not going to get damaged, especially say if you have got a museum or the building that the content is going to be very valuable. A base isolation system can be a viable option. It reduces the level of force that's transmitted to building because it's isolating the building from the ground, and also it reduces the foundation cost due to a smaller forces transmitted to the structure, because since the building is not going to move much, then there is going to be less force coming from the structure to the foundation. Then these are the main advantages of the base isolation system. Then the base isolation system, since it basically allows the building not to move much, it reduces the acceleration of the structure to remain mainly elastic. Then it doesn't get into plastic range. It also provides a control environment for the design of non-structural system and content. As I said, since the building is not going to move much, then the non-structural and content are going to be intact or little damage. The base isolation system is not appropriate seismic design or retrofit for tall buildings because they have high period and they have large displacement. Then when you have got 20, 30, 40 story building, then base isolation system is not going to be a viable option. If you have a low-rise building up to 10 story building, base isolation system can be a better option. And the main reason is that when you have got a tall building, the tall building under the earthquake is going to go under large lateral deformation. You have got large movement, and the base isolation system may not be able to handle such large movement of the structure. A building with complete but relatively weak or brittle load paths is a good candidate for base isolation to keep seismic load within the or below the brittle range. The natural period of base isolated structure is generally more than 2 seconds, and the dominant period of the earthquake is within 0.2 to 0.6 second range. Therefore, there is no amplification of earthquake load since there is no resonance. Then again, we are looking at these 2 seconds for shorter building. We are, low-rise building basically. Then that is possible. But if you have got a tall building, obviously the base isolation system is not going to be a viable option. The next type of enhancement devices is added damping system, and these added damping system come in different forms and shapes. We can have basically these added damping system in the form of high yield steel that are used within the gusset plate of braces. These are gusset plate, and they use this high yield steel that basically connects the braces to it, and they can deform and dissipate the energy of the earthquake. The other option is to basically put the dampers, viscous fluid dampers that they have got oil in them, and they provide reduction of the earthquake forces within the braces. Then instead of putting braces, we are putting large shock absorber. Then these are sort of like car shock absorbers that we use in cars, but they are much larger units, obviously, to be able to take the lateral loads from an earthquake. Dampers. This is a damper, as you see, in a building that's used for seismic resistant design. The next type of device is called tune mass damper. These are used to reduce the vibration mainly from wind or earthquake. We use a very large weight at the top of the building, and that's connected to the springs and dampers. Then the other way of doing it is to use a large suspended weight, and such that it acts like a pendulum. Then it can be either on the top of the building. You can have a big block of weight connected to some sort of shock absorber and some kind of a spring, and it's the mass. Or you can have within the building, you can have a big ball of weight that's basically connected to some kind of shock absorbers, okay, that this basic pendulum can move back and forth. Let me just draw this, for example, like this. Then this pendulum can move back and forth, and these are the dampers. And this is also a damper, and these are springs. And this is a tune mass damper, TMD, and this is a pendulum tune mass damper. Then I can call this a PTMD. Okay, we can also have large tank of water, and the slushing of water basically provide damping of the vibration of the structure. A two mass damper is designed such that the tune mass damper is designed such that it has the same period as the period of the building, and it is tuned so that when the building moves to the right, the tune mass damper, if the building goes to the right, the tune mass damper goes to the left, and the other way around. If the building goes to the left, tune mass damper goes to the right. The same thing with the pendulum tune mass damper, and in this way they can reduce the vibration of the building. They have been used in many tall buildings to reduce the lateral vibration. A large block of concrete was used in New York City Court building. About 400,000 pounds of concrete basically was used there. For type of 101 building, also there is a large ball of lead which is suspended from the top of the building, which act as pendulum tune mass damper. These pictures, these figures are showing basically the tune mass damper used in City Court building, and you can see this is the TMD, this is the damper, and basically the movement of the tune mass damper is such that when the building moves to the right, the TMD goes to the left, and vice versa. And the same thing for the type of 101. As you can see, this ball of lead can move in the opposite direction of the building. This is a view of the type of 101 with pendulum tune mass damper.